welcome everybody, those that are here and also those that are at home. Welcome to this seminar session. My name is Sergio. I will be chairing this seminar session presented by Dr. Hüseyin. He is the principal scientist and group leader at 𝗔𝗕𝗦𝗧𝗥𝗔𝗖𝗧 Center with over 20 years of experience in thermomechanical processing along web design and product development. Dr. Aydin earned his PhD from 𝗔𝗕𝗦𝗧𝗥𝗔𝗖𝗧 University in 2013, and he has authored more than 30 publications and presented his work widely in international journals and conferences. And his research focuses mainly on advanced metallic materials for aviation and automotive sector. And he also serves as an adjunct lecturer at Marmara University in Turkey. And today he's here as the coordinator of the horizontal European project called 𝗔𝗕𝗦𝗧𝗥𝗔𝗖𝗧, where we are collaborating together to that center, CIMNE, and also LTD. So thank you. And
thank you for the nice presentation, Sergio. I would like to welcome you all. Today, I would like to give you a presentation about advancing high temperature applications of additive manufacturing, and also some insights into creep and fatigue and tensile response at high temperatures of these materials. Sergio has already introduced me, but briefly, I just would like to say my name is Hüseyin Aydin. I am currently a principal scientist at 𝗔𝗕𝗦𝗧𝗥𝗔𝗖𝗧, and my area of expertise is alloy modification, thermomechanical process design, which can be includes forging, rolling, and as well as high temperature mechanical test, fatigue, creep, and hot tensile. I also have huge experience about meso and micro scale characterization. Due to nature of thermomechanical processing, you have to also focus on some characterization facilities to obtain desired microstructural and mechanical properties. And my PhD thesis was mostly studying at dynamic mechanical behavior as well as pressure-worthiness and high-speed forming. So today, what I would like to present you is starting with the outline, who we are, who is Metallic and Structural Materials Group inside the 𝗔𝗕𝗦𝗧𝗥𝗔𝗖𝗧. The motivation of this presentation, some case studies I will give you, mostly in post-processing of additively manufactured metallic materials. Then my final case study will be some which I will also present in COMPLAS, and question and answering period. So who we are. Before our group, I would like to say that TÜBİTAK is a national research center of Turkey, established in 1972. Currently, 17 active groups is working from food engineers to computational mechanics, from sustainable economy to energy facilities. We are one of this 17 group focus on metallic and structural materials, 3 teams: testing, structural, and post-processing and characterization. Structural material groups mostly focused on composite and ceramic materials. Casting facilities or casting team is mostly focused on directional and single crystal castings dedicated to superalloys and advanced steels, contamination-free and fully controlled microstructure and investment casting facilities in part-based. What we are doing is actually in our team, what I'm focused on is post-processing and characterization team, mechanical and microstructural properties of metallic materials at high temperature applications, as well as performs pilot scale production in part case. Also, we provide some characterization and find and analyze projects. These are the basic infrastructures from laboratory scale casting, heat treatment, hot isostatic pressure, electron microscopy, thermal analysis, and advanced optical and electron microscopy facilities, and finally thermal barrier coating and concentrate facilities for repair purposes. Okay. Just before the motivation, I would like to give a little bit background information about what we are doing and what I will present today. During the microstructural driven thermomechanical processing, several phenomena can occur. It can be either hot deformation, it can be either post-processing such as heat treatment and quenching, starting from recovery, reorganization of the grains, not too much change in the grain formation or morphology, but release of the stress, residual stresses. Then further heat, we have recrystallization. As you already know, with recrystallization, we have ordered structure, fine grains, and strain-free morphology. And finally, with heat and deformation, we have grain boundary migration and grain porcinic, which can be very effective in our case for high temperature applications. In high temperature applications, we are looking for not only for ordered grain structure or fine grains. Actually, we are looking more coarse grains with which is also prevent the dislocation motion during high temperature and deformation or loading, we can say. During TMP, due to temperature raising, the dislocations become mobile, and most of the creep and fatigue test in high temperature, the main active mechanisms is dislocation motion, grain boundary sliding, or grain boundary diffusion. And the purpose is, at the end of the day, we would like to improve high temperature life or rupture time of the materials. So again, another background information about additive manufacturing, because all the case studies, all the case studies I will present today is additive manufacture samples, mostly superalloys. Advantages and disadvantages compared to traditional methods, not vast amount of production capabilities. There are some multi-material options not available for additive manufacturing, but compared to this, in contrast to this, excellent for complex geometries, no support material needed or shell needed like investment castings. Good surface finish if you know, depending on the material and the process you selected, and post-heat treatment may be required. This is not advantages or disadvantages, but if you are looking for desired mechanical behavior, you have to consider post-treatment applications. The problems in additive manufacturing is porosity. If you are talking of thermal gradient, conventional heat, selective laser melting procedures, porosity, lack of fusion, multiple dimensions, and microstructures inhomogeneity, which we can heterogeneous microstructure, density, fine cellular, because like all the welding or joining techniques, they have lack of fusion problems, and due to layer on layer powder conventional heat applying, we have some issues, localized expansion, as well as because of the rapid cooling, residual stress problems. So if you have residual stress problems in traditional methods like as cast and as forged materials, you can apply stress relief before desired solution treatment, aging, or any kind of heat treatment you would like to apply. So final background information, as mostly already know these things, but slightly I would like to mention creep and fatigue, two different phenomena for high temperature materials, metallic materials. We would like to perform or qualify the materials. One of them is creep, is a time-dependent deformation behavior of metallic material under constant load. Fatigue, actually, probably most of you knows better than me, is a form of fracture. You have a cyclic loadings, both of them under the yield stresses. One of them is the most important parameter is critical resolve shear stress in second stage of the creep, because critical resolve shear stress is higher, means you have less plastic deformation at high temperatures, and not necessarily, but mostly, you have longer life cycles. In terms of fatigue, it's a kind of crack formation, and we can, depending on the stress or loading you applied, on constant loading you applied, cyclic loading, sorry, you can figure out the moment crack propagation, crack initiation, then crack propagation, and the end of life cycle. So motivation of this finally comes. What we are doing, the first two case studies will be effect of heat treatment. We call this post-processing because for aviation and automotive industry, the industry we are most working, industries we are most working is a post-process, and post-processing means extra costs. So it is very important to design a post-processing for a particular part or a coupon sample, it doesn't matter. The first initiation of the industry will be if it is cost effective, if it is optimized, and if we can, these cost effective optimized parameters, if we can obtain the best mechanical properties. So we use some thermodynamic simulations. We are expertise in thermodynamic simulations. We design heat treatments in certain cases using hot compression and torsion tests and figure out the interface times. We are also trying to do some rolling and forging process parameters. But at the end of the day, we are trying to initialize to obtain the final microstructural properties that we can get better mechanical properties. So this study, the first two will be the already completed projects for certain aviation industry. One of them is funded by the actual TÜBİTAK itself, because TÜBİTAK is not on the research center. In our capital, another TÜBİTAK, not the another, but another location we have, which is actually directly connected to the Ministry of Science and Technology, and also it's a PINIC agency. So as a TÜBİTAK MAM, which is in 𝗔𝗕𝗦𝗧 location, if we would like to do some research innovation activities, we can also apply for our own center to get some receipt, which is also connected to the Ministry of Science and Technology. The third one is European Horizon Widening Program, twinning initiation, partners with CIMNE and LTU. And the second one is actually dedicated to a kind of industrial project. It's a part of a master thesis, and it's totally focused on the heat treatment and creep properties of as-built Inconel 718 superalloys. So, Inconel 39, the first study, let me tell you again. The first case is advancing creep performance and oxidation resistance of Inconel 939, alloy fabricated by selective laser melting. It's a PhD study of one of our colleagues in TÜBİTAK. I will not explain you the oxidation resistance part because the presentation is already long enough. So we'll focus on the heat treatment design as well as creep performance. But before that, I would like to mention a little bit about 939. 939 is a very special escape materials. In superalloys, in aviation industry, we define the metallic materials into two groups. First one is escape materials. You partly cast with investment casting methods in a shell. The second is as rolled materials. You cast as an ingot, then forge, or depending on the process parameters, as roll, and finally machine. 939 in this first family is escape materials, and what we expect from this, depending on the usage area, NGV, which we call this nozzle guide vanes, or this or bliss parts, is mostly service conditions work under temperatures, less loads. So there is not too much load, there is a constant load, high temperatures, depending on the area. If it is nozzle guide vane, around 800 Celsius, if it is this part, it's around 750, 720 Celsius. But in this project, we will try to obtain these mechanical or service conditions performance with additively produced. They are all SLM produced materials, selective laser melting, We have several about coupon samples. These are rolled samples, 20 centimeter length, 30 millimeter radius. Then we heat treated them and hot tensile and creep tests. And before that, we look at their microstructures. As you can see, they are dense microstructures, not too much porosity. We optimize these results with an aviation industry partner in this government-supported project. In XZ plane or build direction, we have melt pools, looks like hundreds of or thousands of welding heat-affected zones. And the other is, when you look at from the cross-section, you will see melt bed contours, elongated grains, and dendritic microstructure. So what we design according to using thermocalc, and some experimental differential scan calorimetric analysis, we define certain temperature transformation temperatures for gamma prime formation, solus temperature. So we did some experiments on carbide precipitation temperatures. Three classes of heat treatment procedures. The first one is heat and aging. The other is vacuum heat treatment and aging. And the third one is just to combining of heat and vacuum heat treatment. What is the difference between heat and vacuum heat treatment? Heat procedure is a kind of general standard procedure. It becomes recently a general standard procedure for materials which we are additively manufactured. It's a hot isostatic pressure equipment. As we know, the physical properties of any metallic materials can change or is a function of either temperature or pressure. So in this case, we apply both. If you increase the pressure, the transformation temperatures will decrease. This is a big advantage. You will have much more dense microstructure because of the pressure. You have order structure depending on the isotropic pressure and apply heat. And you don't necessarily need to reach certain about temperatures because of the pressure. So it's very advantageous. But does it work? It's question mark because the quantity. When you do heat treatments, you have two things, as I said before, recovery, recrystallization, and cooling down. So in each cases, it can be either solid solution strengthening or precipitation hardening. You need heating control and cooling control. So for the final grain size, depending on the diffusion rate, segregated alloying elements in the desired microstructures, and finally, order of the grains, which we call this texture. So for anisotropic structures, you need a control in the heat treatment procedure. The issue is that the people misunderstand. When we call this microstructure-driven mechanical properties, what would like to obtain defect-free, homogeneous order structure or microstructure, and depending on the strength you want, precipitate hardened microstructure for superalloys. This is the basic explanation. So we tried 3 experiments. Initially, we performed first 2 and 2 tensile tests before passing the creep and fatigue test. We observed that it doesn't work. So we have to focus more. Basic heap and solution approach as we used in SKS materials doesn't work. So as you can see, the elongation is very low. Strength is in as-built condition even higher than heat treat 1 and 2. That's why we developed several heat treatments with changing duration time, cooling rate, as well as gas fan quenching vehicles. Air gas quenching means kind of furnace cooling or stabilize in the furnace until 850 service conditions, then remove from the furnace and cooling in the air. Gas fan quenching is around under 16 bar or 3 bar pressure, which is close to 113 Celsius per second cooling rate for the material. So the observations were, yes, we are much more dense structures. In some of the cases, especially HT1, direct vacuum heat treatment, we don't have too much recrystallization. Melt contours are still in the microstructure. There are certain intergranular carbides, but we have certain amount, which is expected in 939, more than 65% gamma prime precipitation. It's good. When we look at the other microstructures, HT4, when we increase the solution heat treatment and decrease the second aging, that's an issue because we couldn't dissolve all the carbides like the HT1, but we don't have too much, as you can see, melt pool or melt pad boundaries. We homogenize the samples, solutionize the eutectic regions. We have certain amount of carbide problems, but we have well seen and coarse gamma prime precipitates. In terms of heat plus vacuum heat treatment procedures, again, some shadow effect of melt pool boundaries, not newly oriented grain boundaries. In the melt pool boundaries, we have again carbide phases, but much more finer compared to vacuum heat treatment gamma prime precipitates. When we look at the mechanical properties, first, after improving heat treatments, we have better tensile properties even at high temperatures. We increase the UTS around 900 megapascal, still lower than as built, but the elongation values, especially HT1, HT2, and HT4, which is directly oriented to vacuum heat treatment, control heating, and control cooling. I explained a little bit with HEAP, but I didn't explain vacuum heat treatment. What is vacuum heat treatment? In aviation industry, we have different kind of vacuum heat treatment procedures. You can either use graphite furnaces, there is no resistance heating, graphite, or molybdenum. Full molybdenum is a contamination-free heat shields in general, molybdenum, pure molybdenum, and heating elements is mostly molybdenum lanthanum, and you have pressure ultra high pressure to dissolve gamma eutectics and carbides or lava phases depending on the superalloys, and you have fully controlled cooling environment. The biggest advantage of vacuum heat treatment is you can continuously heat treat it after solution heat treatment, which you can obtain solution strengthening in matrices, which is gamma. Continue directly to aging steps. You can ultra-fast quenching, then go high the subsurface temperatures to obtain desired precipitates, which is gamma prime in its case. So when we look at the creep properties, we have certain heat treatment and certain results, and depending on the perspective what you are looking for. As I said before, 939 can be used in different parts. If we are looking, which I'm interested in NGV parts, which is temperatures much more higher and its loads are extremely low, you are looking for not the life amount you obtain in creep test. You are looking for the creep percentage or plastic deformation after the life rupture in these materials. In the case of HT7, it is less than 1% creep strain after 200 hours, which is a very good and not comparable but close to S-cast NGV values if you decrease the applied load during creep condition. This test is 750 Celsius. We apply 350 megapascal. In general, we apply in this temperature to service conditions is 144 megapascal, which is double of the stress. Plus, we also try to see the performance of HT7 at 8750. When we increase the temperature, we saw that it is even better and close to, it's much more closer to the casting conditions. Still not comparable because investment casting is a very state-of-art casting methodology, but applicable in the case of aviation industry in certain cases. It's more than 40 hours, still plastic deformation or creep percentage is less than 1%. As I said before, This is mostly related to rafting mechanism, dynamic precipitation of gamma primes, because initially they can be cubic and they precipitate during the service condition as a cubic secondary gamma prime, or in the case of 718, which I will explain later, gamma 2 prime. So in any case, the Stochastic motion, gram boundary sliding, or gram boundary migration, which mechanism you are looking from defines the critical resource shear stress, which requires less plastic deformation during the second stage of the creep mechanism. In creep mechanism, there are still 3 stages. Primary creep stage, which is parabolic. The second is steady state, and third is like fatigue, is a rupture area. Third stage, we call this, which is unexpected or unpretended rupture mechanisms occurs. But in the case of HD7, it is less than 1%, even after 4 hours, 8 degrees Celsius, which is not applied for these materials in these temperatures, and 250 megapascal. Anyway, let's finish. We did some TM characterization just to see what we can see. This was interesting because, as we know, in fracture mechanisms, in the creep, we can see everything. All the mechanisms, grain boundary slating, vacancy replacement, grain boundary migration, element segregation, or we call this, as well as dislocation motion. In this case, we saw dislocation glide in dislocation networks. In the newly nucleated grain boundaries, we see some multiple sticky pulse and cavity nucleation. And inside, even they cut through the gamma prime precipitate, some tunings in this microstructure. And due to rafting, we have gamma prime coarsening. As you can see, sorry, maybe no. These are the small little spherical ones as secondary gamma prime formations, which also not improves but postpone the fracture mechanisms during creep in these materials. Summary, at 750, we saw dislocation shearing through gamma prime, which is stacking fault formation, or in some cases, some superalloy people say that under-phase boundary formation, because it is not like steel. These sticking faults or tunings can cut through the precipitates compared to in steels. They were in general partial dislocation between two intergranular grain, which is austenitic phases. But here a little bit different. Gamma prime combining of precipitates and rafting mechanisms. It says no rafting, but as you can see, some people say that this is a gamma prime coarsening. Some people say rafting. In this thesis, my point of view and my colleagues' views were totally different. I believe these are kind of rafting, but the other people think that they are just gamma prime coarsening. But in 850 Celsius, we totally clearly see the rafting mechanisms, some intergranular cavitation, and micro crack initiation, which is normal at these extreme temperatures and lows. So the second one, again, it will be mostly creep and hot tensile. This is the creep equipment we have. In general, we use high temperature mechanical testing is extremely difficult compared to room temperature tests. You can do high cycle fatigue at room temperature with easily in mechanical creeps without contacting any thermocouples, as well as you don't have not I will say difficulty, but luxury of contacting extensometers. But high temperature test, it's a requirement. This is a leverage extensometer, which is very specific, dedicated for creep machines. It is much more accurate and reliable than the in-contact extensometers. This fully accredited and Additive certified furnaces -+3 Celsius. So if you are doing this superalloy high temperature creep or fatigue tests, you need reliability. So at the end of the day, we produce the results for either industry, automotive or aviation industries, or either people like you for as an input parameter for your model. So reliability is the most important thing. this is a kind of different scan strategy, 718. In one substructure, we produce coupon samples. Then we look at the microstructures. In the building direction, we have melt pools. In the cross sections, we have melt pads. But here, again, I would like to mention about something. Constant strain rate test is actually the stress tester of the material. As you know, with increasing temperature, stress release ductility, strength decreases, ductility increases. But creep test not necessarily. As I said before, the most important in the creep test is the creep strain or plastic deformation you obtain, or the resistance of the material against creep strain. Let's define like that. So again, some thermodynamic studies, some differential scanning calorimetry analysis. We obtain transition temperatures. We found the gamma prime formation. Even gamma 2 prime, we go with it because during temperature and deformation, gamma prime is promising to transformation of gamma 2 prime. The Child cooling diagrams, which is important, we would like to see which order they will follow. As you can see, the gamma transforms the first gamma prime, then with further heat and deformation, gamma 2 prime. The problem in 718, this is a 718 material, as I said before, effect of heat treatment, additive porosity in Inconel 718, levels and delta phases. Yes, further heat and heat treatment procedures, we can obtain better mechanical properties, but there is a risk for formation of, according to Child coolings, solidification graphs. We observe some formation of levels and delta phases, which is undesired intermetallics in the microstructure to decrease mechanical properties of these materials. In this stuff, we designed 3 heat treatment and compare with the standard conditions. Homogenization, what we call this actually stress loop. It's just a stress loop because additive manufacturers all comes with residual stresses. For example, I will present a little bit later. In our case, these materials, is the same conditions with some projects, but this was different project. It's the same equipment, EOS M290 produced them with a certain of volumetric energy density. Same scanning strategy, Z direction they built it. And at the end of the day, we observed that it's more than in the not machining condition, around 600 megapascal residual stresses. In machine condition, the situation is different. I will explain in the FASAM a little more why it is. Anyway, we look at the compositions. As I said, we couldn't escape from the level phases. And with creep, we even after creep and heat treatment, with level phases, we saw some delta phases as well, level and delta phases. But after heat treatments, we have much more ordered morphology after homogenization and heat treatment. Newly nucleated grains after recrystallization, even because of the annealing. We have annealing twins as well. In terms of higher temperature heat treatment, we have much more aqueous grain formation. The importance of the Inconel 718 and aqueous grain formation is Inconel 718, in contrast to 939, is a rolled elbow. What you will use is impeller, manifold, or some parts working under fatigue force. What you need is aqueous, not grain porcinic in this material. So, as you know, we are working on fatigue properties in FASAM project. That's why in this project we focus on creep properties. Yes, it is true that these materials are not obliged to work under creep conditions, but we just try to figure out what is the capability of additively manufactured Inconel 718s after heat treatments in creep conditions. So first we did hot tensile tests. Is actually even as build conditions 718 technology in additive manufacturing developed quite fast. It's quite good mechanical properties, but we improve their strength much more with heat treatment conditions and optimize ductility. So let's go to creep properties. As you can see, several properties which I like a lot, 1090 and 1090 plus 954. 954 is actually solid solution temperature before aging. The issue is that after stress lift, or some people call this homogenization, what you would like to estimate? You would like to prolong its plastic deformation and life cycle under creep, or you would like to obtain less plastic deformation during creep. As I said before, most of the people prefer this one. I prefer this one, the blue one, not the, I think it's red or pink. It looks like a pink from your side. I don't know. In my case, why I like less plastic deformation, because the temperature 649 is service condition temperature, but the applied wheel load for grip test is 650 megapascal. You will never use 𝗔𝗕𝗦𝗧𝗥𝗔𝗖𝗧 in 650 megapascal. With safety coefficients, the maximum applied load for 𝗔𝗕𝗦𝗧𝗥𝗔𝗖𝗧 is around 360 megapascal or 375 megapascal. So less plastic deformation means you are in the more safe conditions, no plastic deformation. Another issue for 939 and 718, any of these materials, let's say that it's prolonged in these harsh conditions is 140 hours, they will replace half of this cycle. They will be replaced. So if there is no plastification, no micro cracks, no crack propagation, no fracture. Let's go to results. Why I'm saying this? Fundamentally, we know that creep is a function of critical resolve shear stress. This is a theory of coming from half of the theory coming from Holloman equation, half of the theory coming from Johnson-Cook equation, which dynamic conditions. But at the end of the day, higher the critical resolve shear stress in the steady state region, higher the creep performance, or more resistance to creep elongation of the materials. As we can see, HD9 1090 plus 954 is the highest critical resolve shear stress. This is tricky because in these materials it is very difficult to find the steady state, because superalloys is slightly different from other materials. Why? In general, creep, it looks like a reverse of the SN curve in fatigue. You have a parabolic region, steady state region, and rupture. Let me return this one. There is no steady state region in superalloys. Or, when I say this, because in the last conference in MMC, people didn't like this definition, which is right. Let's say that it's a very short amount of time steady state region. That's why we focus on the steady state region. For highly elongated samples, you can see a little bit like HD954, but or as built conditions. But rather than this, it is too much noise to calculate the steady state critical shear stress. In terms of summary, we have microstructures as LMX is the difference from cast and rod counterparts, because this is a cast and rod superalloy. Metal structure displayed refined cellular columnar pattern distinguished by irregularity shaped lavage phases. In some indentate areas, we also saw delta phases, which is everything we want. I'm stating again and again this one because in casting, we have an opportunity to remove these phases with special casting equipments like vacuum induction melting. And before that, if you do vacuum arc melting to remove phosphate and sulfur phases, it will be even better. So triple melting is the best method for 𝗔𝗕𝗦𝗧𝗥𝗔𝗖𝗧, and it provides contamination-free, intermetallic-free microstructures. So still, additive manufacturing has issues with them. Why? I would like to stay just 1 minute more in this second results. The biggest problem in additive manufacturing, we cannot use this material composition as we use in casting and rod processing. So we have to make, especially in terms of face-centered cubic materials, like superalloys, nickel-based superalloys, we have to make them weldable. So what we are doing, we increase the chrome ratio a little bit, decrease the carbon a little bit, which can be seen. But in contrast, we need to increase, because there is a ratio of titanium, aluminum plus carbon, increase titanium and niobium ratio, which provides very much segregation and formation of new intermetallics. And still, it's a welding procedure, joining of powder to powder. Carbon is one of the most active elements in the microstructure. It is activation energy very low, so whatever you do, like just put an etui which is mostly 120 Celsius, carbon will start to segregate. That's the issue. If you are doing additive manufacturing, you should think that, I keep saying that, it's a welding methodology. That's why new methodologies are coming by, which is my favorite, cold spray. It's coming because it's just a kinetic mechanization, low heat. It's a very effective way, and it will be very popular in the future. If you are big counterparts, DED still is the most attractive one, but rapid prototype and small parts, SLM is the best. But in certain materials like metals like titanium alloys or stainless steels, EBM can be method of choice. So final summary, heat treatments, the arc-shaped microstructure features were replaced by aqueous grades. This is one of the biggest success of this post-processing study. And we have a stable gamma matrix straightened by gamma 2 prime or gamma prime faces, which can easily see from grip results. And finally, FATSAM. I will keep it a little faster because it's a very long case study to present. What we are doing, FATSAM, just motivation. We have three partners, LTU, CIMNE, and us. We are applying mostly experimental features and provide data for CIMNE and LTU. LTU do the AM calibration, CIMNE do the upgraded fatigue model for these materials. I'm saying upgraded because most of the studies are currently high cycle. In this project, we will do low cycle fatigue, which is strain control, plus we will do elevated temperatures, which is 3 different temperatures in additional room temperature, which can count for 4, plus 3 different strain rates. So multiplies for each temperature with 3 different strain ratios. So let's continue. These are the S-produced part, SLM. This is the substrate removed with EDM. XY plane, which is a cross section of the melt pads, build direction, melt pools. It's very compact, less than 0.1 or 0.2% porosity, but compact it is higher residual stress it is. As the schematic of the fundamental, desired additive manufactured structures, we have aqueous grade with columnar structures, aqueous with columnar structures, melt pool boundaries, fine cellular structure, some level spaces. Still, we cannot escape from it. And the beauty is when you increase, as I said before, niobium and titanium or aluminum ratio is very important for the level pieces. When you try to increase the weldability, you cannot escape these materials. So porosity as built after fatigue and after hot tensile, it's still less than 0.1%. So it's extremely compact. The maximum pore size is around 3 micron maximum. Residual stress is actually, 0.3. And the average, this is top center and bottom of the samples. The average, let's say that 624 megapascal minus plus tensile. 2 comments. These are powder ones. As I said before, we said including room temperature, For temperature, 3 strain ratios. These are for the powder one, standard additive manufacturing procedures. But we are in the future studies, currently we already started, but and materials are produced. We are doing powder 2 and powder 3 as well. Powder 2 and powder 3 is higher VED value and lower VED value, which means higher porosity and lower residual stresses. But another comment, when we machine this sample, we are still working on it, but our initial insights are due to this aqueous columnar structure change, as well as machining effect, which is release a little bit amount of residual stresses, the tensile residual stresses going from 624 to down, and compressive minus around 300 megapascal compressive stresses. But we are still working on it and we need to confirm it, but we will see the results in this project. This is one of the most important parameters we would like to provide, during fatigue modeling. Tensile results, quite good, even when the increasing temperature is more than 50% elongation. There is because in our previous 718 projects, we never scanned that much of area to obtain fatigue matrix. We observed that at around 750 and 800 Celsius, a slight microstructural evolution, which haven't we confirmed yet, but probably due to dynamic recrystallization under temperature and loading, and we have increase in strength and yield of the material, and extremely decreased ductility, even less than lower temperatures. This is probably strain hardening of the material due to dynamic recrystallization of the material, because the service condition of this material is 650 and we tried until 1000 Celsius. So these are the basic fatigue results we have got. Our software can provide history of stress and cycle, or strain, amplitude, or cycle. Also, we have any kind of strain control parameters. We have in-touch extensometers, 3 thermocouple connected to threads at the center of the materials, minus plus 3 Celsius, and coolings in the grips. This mechanical, it's not a mechanical grip, it's a hydraulic grip. For high temperature applications, it's a requirement to use hydraulic grips. You cannot do high temperature mechanical test if it is not force control test. In force control test, you have advantages. You don't necessarily need to connect thermocouples, or you don't need to use in-touch extensometers. And also just per cycle results, half cycle results, final cycle results. For each hysteresis, the advantages of strain control test and extensometers are this. Just tell me the cycle you want to see, and I can show the hysteresis loop or strain amplitude and stress amplitude with displacement ratio or strain ratio. This is the biggest advantages using extensometers and thermocouples. With increasing temperature, we observe that the strain energy is increasing. Just is due to some cyclic hardening in 800 Celsius, we have a less strain energy than 650 Celsius. For first and half cycle and crack initiation, when we obtain higher displacement, obtain 800 Celsius, which is expected. And even at room temperature, we low strain levels, we didn't see any deformation, but for high cycles, because this is quick, after certain amount of time, it's uncontrolled deformation mechanisms for fracture mechanism for these materials. I will show some microstructures, and with the strain ratio increase, some strain energy observed with from first cycle to crack initiation area. These are the strain rates for each materials calculated, and crack initiation cycles. In general, most of the studies we use half life cycles for predicting fatigue life of the material. But in this kind of equipment we have, we can also provide you the crack initiation cycle. And with crack initiation cycle, we can see the softening hardening ratio above 0. As I can say, the most interesting one is here. There is no 800 Celsius, and it is all stable in this softening region, and then suddenly drops. When we look at the number of cycles and stress amplitude, we will improve this graph. Two things important. In strain control low cycle fatigue tests, you don't need necessarily to obtain SN curve. In general, we use SN curves, isn't it? But here, you can obtain EN curve, which is, I believe, much more useful if you are doing some ANSYS design for part specific or something like that. And that's the biggest advantages. I can go to the phase diffraction analysis and complete it because we are almost done. As you can see, the room temperature crack area started with different areas. There is a crack initiation and crack propagation regions, but certain amount of time you have unpredicted failure start and catastrophic fracture. So 650 Celsius, same strain ratio. We have less area, but clearly we know the point. And in general, microcracks follow through the multiple boundaries, which is expected, which is a hot delamination for S-built structures. This is no heat treated. For some, there is no heat treatment. There is no post processes. And we want to look a little fracture analysis in macro regions to obtain what we see is a strain with increasing strain ratio. We have much more ductile and shear active fracture mechanisms. The most interesting one, which I like, they call this strain stripes. Some people say that diffusion bands, dislocation bands. I would like to say dislocation bands and hot tearing. I would like to say delamination. Why? Slightly different. These are the, let me show you, pore. Mostly lack of fusion, not gas pores. Through the follow of the gas intergranular multiple boundary, not the boundary, intergranular multiple boundary, and delaminate at the center of the materials. It's a highly dislocation localized zones. As you can see, this is multiple boundary. I can show you like that. And these are slip bands, which delaminated or teared intergranular of the multiple boundary. It is very interesting because most of the fatigue tests, you don't see that. People started to comment easily as the previous picture because you need to go much more deeper. Multiple boundary, macro crack initiation. But when we go, this is again 0.4%, but higher magnifications and different scanning area, we will see these are slip bands and hot tearing regions. So there are 4 different results. Fatigue crack origins primarily involve the pre-knit defects such as lack of fusion, gas pores, particles, or microstructural imponentiality, but crack propagation region exhibit a mix of fatigue citations and ductile tearing. This is one of the first observation, and there is only 1 or 2 literature studies mention it, but not detailed research about it. And also specimens displayed cleavage crack initiation at high temperatures. Crack initiation sites were found to be connected to adjacent sites via shear lips, which merged to form larger cracks that propagated through the material, which is normal for any additive material at high temperature applications and fatigue tests. So this is what we'll expect. And again, the multiple structure was displayed as a refined cellular columnar pattern and distinguished by irregularly shaped level spaces. Final comment, in Conan 718 in this project, we are focused on as-built condition, but without any heat treatment or post-processing, you cannot escape as-built conditions levels and the databases in Conan 718 or most of the other metallic materials. So I would like to thank you and thanks for attention and patience.
Thank you, Hüseyin, for the presentation. It's one, so we have time for a couple of questions maybe. And if any, here in the audience, I'm not sure if somebody from home in case.
Home or office?
If not, I have several comments. We can discuss them during lunch.
Okay.
I would like to ask you a question about the feasibility of applying certain of the heat treatments that you mentioned, that you're applying at a sample level, then to component level and so. And if you can then demonstrate that, which is the, let's say, effect, or that the effect that you have observed at sample level can be then obtained at the component level.
Actually, we had, as I said before, the second case was for an industrial support project. We already obtained that results, and they are applying some of the heat treatments. Including 718 is the most widespread superalloys in aviation industry. And honestly speaking, they are not using without any heat treatment currently. But most of the projects or most of the literature study is now in as-built conditions and machining, because post-processes brings much more cost. And as you say, in Conal 718, including stress relief, you have 3 steps or 4 steps heat treatment. Nobody wants to apply this. So this is why the industry was expectation. Okay, you can do some heat treatments, and even we can conduct these projects if we have some samples left or coupons left. I'm not sure now, depending on the current fatigue matrices, if we can complete it successfully. But people say that, industry especially say, okay, I know this, it's getting better with post-processing, but then it says it's specified rotalers. So what is the advantage of additive manufacturing? Yes, it is rapid prototyping, and you cannot do mass production. So this advantage of additive manufacturing becomes disadvantages. This is why they are funding universities and research center industry. How is it possible to use in as-built conditions with certain machining effects, maybe a stress relief, not heat treatment, nothing more than. This is why it's supporting the industry, and so many topics are coming for as-built conditions. I believe there are some possibilities even as-built conditions, because I never see that much dense microstructure. Because in our previous study, these samples are in-kind contribution of TI. It's a Turkish aircraft engine industry in Turkey. With time, they also improved their stuff. They are currently very good in additive manufacturing technologies. And simulating in our first project, as I said before, master student of one of my master students in the research facility. Now she's working in another aviation company. We didn't have that much good in Conal 718, and it's improving and improving and improving. Now, just recently, SLM Solutions is an additive manufacturing company with equipment for additive manufacturing. They say that we are adopting a kind of how can I say, post-heat cabin after the additive manufacturing, just to relieve stress. 20 minutes, 600 Celsius or 700 Celsius, just to relieve stress, relieve stresses of the materials coming from additive manufacturing. And the technology is going there. So we have to focus on a reliable fatigue model, because we don't have even creep model. I did so many creep tests, I did so many fatigue tests. As I said before, my facility not only develop materials, but also we are testing and characterization facilities. Let me tell you, so many people probably working on metallic additive manufacturing, probably they know better than me the fundamental knowledge of the additive manufacturing. But I can assure you, nobody tested additive manufacturing metallic materials as me. Just recently, I calculated more than 700 tests in the last 5 years. Stainless steel, superalloys, aluminum alloys, which I don't like, and as well as titanium alloys. because sample preparation, especially titanium is reasonable, but aluminum is crazy, especially aluminum, tin, magnesium, silice, EBM materials. You cannot polish them. You cannot see in the microstructure there are always flakes. But the potential of these materials is going for as-built conditions. They don't want heat treatment. I would be happy. This is my expertise area, thermomechanical and post-process. I can heat treat it or deform, hot deform anything, but they don't like it. They say that it's cost effective. Just improve as-built conditions. So to improve as-built conditions, we need to figure out how to fracture them under high temperature applications, creep models, and as well as fatigue models. This is one of the most important effect of FATSAM project, because there is no reliable model. There is no that much experiments in the literature. Even results will be makes future effect. Maybe companies are doing, but they are not publishing. So it will be open access. Yeah.
Okay. Thank you.
No problem. Any question?
Any other question? Yeah. And if not,
I
we will
can
thank again Hüseyin for the next call.
Thank you.